G'day, in this video we're going to be focusing on energy and its role in mechanics. Energy is what drives force and force is effectively what drives motion. So our focus is going to be on how energy is connected to kinematics and dynamics. So we're looking at dot point 2.2.3, Module 2 Dynamics, and the inquiry question still, how can the motion of objects be explained and analysed? We're going to start unpacking these equations which are about work, which in our context is essentially a measurement of kinetic energy that's actually being applied to an object. And we're also going to look at gravitational potential energy and how that can either build up or be released depending on the vertical motion of an object. So what I would like to do in this video is give a definition of what work actually is and show how the equations for work are able to connect that idea of motion and energy as well as force. And then also look at how in situations where gravity is involved, the changes in the energy of an object. So our definition for work essentially is the energy that's transferred into an object when it is moved over a distance. And to determine how much work has been done, we need to think about two things. First off, how much force was put on the object, as well as how far did it travel. Work is a measurement that is done in joules, so really it is representative of kinetic energy that's actually being used up or applied. Something to note is that when a force has been applied to an object and it doesn't move, in other words, displacement is zero, then no work is done, and you'll see that in the equation in the following slide. Something that I wanted to do before looking at the equation itself was reflect a little bit on the work done in being able to move an object in two different ways. Essentially, we're going to lift an object and use a ramp to move an object up and onto a raised platform. There's going to be two ways that we can go about it. Here we'll have a little object X on one side of the platform and a copy of that same object a little bit further away. Now, either we can lift the object and place it on top, or we can walk the object along a ramp. Here in this first scenario, the displacement of the object is quite small compared to the displacement which would be required to be able to get the object up and on top of the platform. However, to get this object to be able to actually get lifted up and go against the force of gravity so directly, a very large force would be required to be able to lift the object onto the platform. In comparison, the amount of force which would need to be applied to push the object up over a longer distance would be smaller. So in the first example, we have a large force being applied and a small displacement. And on the other side, on the right-hand side, we have a small force being applied over what is quite a long displacement, relatively speaking. And what's interesting is the amount of energy required for both should in theory be equal, that the work of in the first scenario should be equal to the work in the second scenario. And that is expressed in our work equation. Essentially, work is equal to the perpendicular force applied over a displacement. And here we should note that we are talking about a force which is perpendicular to the displacement itself. It should also be noted that if we are analysing a force which is not perpendicular to the displacement, then we can find that force by multiplying the force vector by cos theta. And I'll show you what that looks like. So let's say I had a box attached to a string and was pulled to the right, but not just to the right, but also in a partially upwards direction, meaning that we have a force being applied at an angle. Assuming that a force has not been applied enough to completely lift the box off the ground, then what we would expect to see is a displacement here, which only goes towards the right. And here, thus, the force itself, as well as the displacement, are no longer perpendicular to each other. So what we would need to do is undertake a little bit of vector analysis to determine this. Essentially, we have our force, which is going in the up and right direction. And this force can be broken up into two perpendicular components. Here, this force at the bottom would be equivalent to F parallel. the force of the hypotenuse being the applied force. If we were to know the angle in between the applied force and the parallel force, we'd be able to apply some right angle trigonometry here to determine the parallel force to the direction of the displacement. Here we could use cos and identify that cos theta would be equal to adjacent over hypotenuse, in other words, the parallel force divided by the applied force. And to rearrange to make our parallel force our subject, what that would be equal to is the applied force times cos theta, or to make it look a little bit more similar to our work equation, F times cos theta. And that essentially is what's getting applied here in our second version of the work equation. In both circumstances, effectively, we are multiplying the parallel force to the displacement vector. We are multiplying the displacement of the object by the parallel force, which is being applied to the object. In a very similar way, we can also look at how gravitational potential energy can change. And that's probably best visualized through the act of weightlifting. When we're looking at the change in gravitational potential energy, there are a few variables at play. One depends on the mass of the object, another the acceleration due to gravity, as well as a change in height of the object. So I want to draw some parallels to the work equation which we did just look at. First off, delta U is also measured in joules and is somewhat equivalent to this idea of work. mg we know is equal to force, which is quite similar again to our work equation, and delta H is another way of representing S, our displacement. Something to note though is when we're focusing on gravitational potential energy, really what we are saying is how much energy is building in an object as it is raised more and more and more above the Earth. Thus, there's energy stored in the object which could be converted into kinetic energy if whatever is supporting it was to go away. Let's just do a quick calculation to show what I mean. In this scenario, let's just imagine that this weightlifter has lifted the object to about 1.7 meters up in the air. And while I don't know exactly what weight is being lifted by this person, let's say that the combined mass here is equal to 200.0 kilos. So to calculate for delta U here, the change in gravitational potential energy, what we will need to do is substitute all values in. So here, delta U is going to be equal to m, which is 200 kilos, times g, which is 9.8, and times delta H, which is 1.7 meters. And this is equal to 3,332 joules of energy. Effectively, what that means is as the weights have been lifted up, it has gained 3,332 joules of energy as gravitational potential energy. Now, the converse to this is to start thinking about what would happen to the energy of the weights if they were to be dropped. In that case, delta H would be equal to negative 1.7. In other words, if there is a gain in height, then delta H is positive. If there is a loss in height, a drop in height, then delta H is negative. However, the mass of the object and the acceleration due to gravity remain the same. In this instance, we would say that delta U is equal to 200 times 9.8 times negative 1.7, which would be equal to negative 3,332 joules. In other words, if this object was to be dropped after being lifted to this height, then the weights would lose some of its gravitational potential energy. It's the same in magnitude to what it gained when it was being lifted. And as it drops, those 3,332 joules of energy will be converted into kinetic or moving energy, which will cause it to drop all the way back down to the ground. Thank you very much. In the next video, we're going to continue on this energy train and making some more connections between this idea of energy and motion. But until then, have a good one.